Welcome back to part G of this very long lecture on quality control, and this is the last one. So we began our study of statistical process control by saying there were two primary questions that need to be answered. Is the process in control? We looked at all of the different methods. We looked at control charts. We did run tests, and all they're trying to do is come up with the question, is the process in control? Well, actually, there's really a question that's kind of even more important than is the process in control, and the one that we should ask first, and that is the process capable? Is the process capable? Capable of what? Well, is it capable of producing a quality part? And just like the other question, this is a yes or no answer. And if the answer is no, then we've got a problem. And we have to work on the process to improve the process until we get a yes answer. So before we can implement control chart, we need to first establish that the process is even capable of producing a quality part. And if it's not, then we need to study why that is and what can be done to improve the process and reduce the variability and other things so that we do have a process that truly is capable of producing a quality part and meeting the quality specification. Then and only then can we ask the question, is the process in control? In other words, is it still capable today, just like it was yesterday, of meeting the specification? So this slide shows three different normal distribution curves, and on each one we see two horizontal lines, and those represent the specification limits for what we are measuring. So we're going to be measuring something that's going to tell us whether or not we're doing a good job or not. And whatever it is we measure, there has to be some type of tolerance associated with that measurement. It's unreasonable to expect that everything will be exactly that same value. There could be little small deviations from it that would still be okay. So the upper specification is what is the maximum measured value that would meet our definition of quality. And the lower specification is what is the lowest measured value that still falls within our definition of quality. And of course, anything in between this lower value and the upper value would also qualify as meeting our definition of quality. So if you look at the upper left-hand corner, you can see that the process standard deviation, the dispersion of the data, that there's quite a bit of data that falls to the right of the upper specification and to the left of the lower specification. So any measurements that falls to the right of the upper specification and to the left, those are defects. Those are defects. So that process is not capable. It's not capable of producing a quality part because there's too many things that could happen that would be defective. Take a look at the normal distribution curve in the upper right-hand corner. Now this is a lot better. So now we have the upper and the lower specification limits that the process width falls pretty much between those two values. So there still could be a few things that fall to the right of the upper specification and to the left that would be defects, but the majority of the things in our process are going to fall between the upper and the lower and will be a good part. Finally, the diagram at the bottom. Now, this is really good. This is excellent process capability, where it's almost impossible to have a defect, that the process falls well within the limits of the lower specification and the upper specification. So essentially, anything we do in the process is going to be good. So that is excellent process capability. So let's apply this to our case study. So again, we're talking about steaks that were cooked medium. So the internal temperature for a steak cooked medium, the ideal temperature is 150 degrees. But there is a tolerance associated with that. We can't expect every steak to be exactly 150 degrees. So we've set a tolerance of plus or minus 2 degrees for this specification. So 150 degrees plus 2 degrees is 152 degrees. That's our upper specification limit. And 150 minus 2 degrees is 148, and that is our lower specification limit. We further know, now assuming that we've been in business for a while, and we further know that on steaks cooked medium, that the average is about 150, but the standard deviation, one standard deviation for those steaks is about 1/2 of 1 degree. So the question is, what is the process capability of the grilling process at Deluxe Super Steakhouse? So we have two formulas, but we're only going to be covering one in this chapter. The other is just a kind of a special case of this. I think this is the important one here. This is the one that I want you to be able to understand and do. And it's called CP, or process capability. And the formula is shown in this slide here. Now, instead of using the term specification limit, the textbook has used the term upper tolerance limit. So it means the same thing: upper specification, upper tolerance limit, lower specification, lower tolerance limit. So the difference between those two divided by 6 times your standard deviation. So we'll plug in our values into the formula. So the upper specification or tolerance limit is 152 degrees. The lower is 148. Standard deviation was 1/2 a degree. We multiply that times 6. We take the ratio, and the ratio turns out to be 1.33. Now, in process capability, this is one of these instances where there is a magic number. And the magic number just happens to be 1.33. What that means is that the upper specification limit, there is 33% distance, 33% distance between it and your entire process. Six sigma is pretty much your entire process. 3 standard deviations on one side of the mean, 3 standard deviations on the other side of the mean. So if the calculated CP is greater than or equal to 1.33, then we conclude that the process is capable. If the calculated CP is less than 1.33, we make just the opposite conclusion, that the process is not capable. And the 1.33 was an agreed upon number from various quality organizations and experts in this field of statistical process control that came to a mutual understanding that this is a good number, and if you have this number, then by definition, your process is capable. So, statistical process control. It's been around for almost 100 years. Walter Shewhart gave it to us. We all owe Mr. Schuhart a great deal of gratitude for the work that he did. It is through statistical process control that all of us are able to enjoy the standard of living that we enjoy in our country. We're able to buy products at a reasonable cost because companies use statistical process control to control their quality and to keep their costs as low as possible. Statistical process control certainly works for manufacturing companies, but it also can be applied to the service industry as well. So it works for both of them. So regardless of what you may do, you could do statistical process control in the banking industry if you wanted to. Well, this is the end. So I know you've been looking for this slide for some time now. So there's no more parts to this chapter to do. If any of these still seem a little confusing to you, be sure and go back and review them. You will have homework on this chapter. You will have to do these same things on exam purposes. So take a look at it more than once, and you may also want to read the textbook as well if you feel like they will help you. So this concludes Chapter 10.